There's something almost magical about the way light travels across the universe to reach us, a journey that takes millions, even billions of years. But what if those shimmering colors we see in distant galaxies aren't just pretty cosmic decorations? What if they're actually a secret language, whispering stories about the birth of stars, the dance of galaxies, and the very fabric of space itself? Tonight, we're going to crack that code, because hidden in those subtle shifts of color, those tiny changes in hue that most of us would overlook, are clues to some of the universe's greatest mysteries. This isn't just about what galaxies look like, it's about what they're telling us, and the story they're sharing is nothing short of extraordinary. Think about the last time you watched a sunset. The way the sky shifts from blue to gold to deep red, it's not just beautiful, it's physics in action. The same thing happens with galaxies, but on a scale so vast it's almost impossible to wrap your head around. When astronomers peer into the depths of space, they're not just seeing snapshots of distant worlds, they're reading a cosmic timeline where every shade of red, blue, or violet reveals something new. A galaxy tinged with blue might be a stellar nursery bursting with newborn stars. A reddish hue could signal an older, quieter galaxy, its star-forming days long behind it. And sometimes the colors don't match what we expect at all, hinting at forces we're only beginning to understand. So how do scientists decode this celestial language? It's not just about looking through a telescope and taking notes. It's about cutting-edge technology, from space-based observatories to supercomputers that analyze light in ways our eyes never could. And the discoveries they're making are rewriting what we know about the universe. These color shifts have revealed galaxies colliding, dark matter bending light, and even the fingerprints of the universe's expansion. But here's the most thrilling part. We're only scratching the surface. Every new observation peels back another layer of this cosmic mystery, and what we find might change everything. So settle in, because by the end of this journey, you'll never look at the night sky the same way again. The universe is speaking, and it's time we learn to listen. To understand why a galaxy's color holds so many secrets, we need to start with the science of light itself. Think of light as a cosmic fingerprint. Every beam carries a unique signature, encoded with information about where it came from and what it passed through on its journey to us. When astronomers point their telescopes at a distant galaxy, they're not just capturing a pretty picture. They're dissecting that light, splitting it into its individual colors like a prism revealing a rainbow. But here's where it gets fascinating. Tiny shifts in those colors tell stories no human eye could ever see unaided. Take redshift, for example. Imagine hearing an ambulance siren as it races past you. The pitch drops as it moves away, right? Light does the same thing. When a galaxy is speeding away from us, its light stretches, shifting toward the red end of the spectrum. The faster it moves, the redder it appears. This isn't just a cool trick of physics, it's how we first discovered the universe is expanding. But redshift isn't the only clue hidden in light. The specific mix of colors also reveals what a galaxy is made of. Young, hot stars blaze with blue light, while older stars glow redder, like embers cooling in a cosmic fireplace, and if certain colors are missing entirely. That's the smoking gun of gases and dust absorbing light along the way, like a celestial shadow revealing the galaxy's hidden structure. What's truly mind-blowing is how far this science reaches. By measuring these color shifts, astronomers can calculate not just how fast a galaxy is moving, but how far away it is, essentially peering billions of years into the past. A slightly blue-tinted galaxy might be relatively close, its light only a few million years old. but a deeply redshifted one that's a message from the early universe, sent when galaxies were just beginning to form. And sometimes the colors don't match any expected pattern, hinting at bizarre phenomena like supermassive black holes or dark matter warping space-time itself. This is why astronomers obsess over every nanometer of color, because in those subtle shifts, the universe whispers its deepest secrets. Redshift isn't just a quirk of physics, it's the universe's way of keeping a diary. Picture this: every galaxy's light is like a message in a bottle, drifting across the cosmic ocean. But as space itself stretches, that message gets warped, its words, or in this case, its colors, pulled toward the red end of the spectrum. This isn't some abstract idea. It's the very reason we know the universe is expanding at all. Back in the 1920s, Edwin Hubble made a discovery that shattered our understanding of reality. By measuring the redshift of distant galaxies, he realized they weren't just floating in place, they were racing away from us, and the farther they were, the faster they went. It was as if the fabric of space was stretching like warm taffy, carrying galaxies along for the ride. But redshift isn't just about speed. It's also a cosmic ruler, letting astronomers measure distances so vast they defy intuition. Here's how it works. The more stretched a galaxy's light appears, the longer that light has been traveling through an expanding universe, meaning the galaxy itself must be farther away. It's like listening to an echo in a canyon. The longer the delay, the greater the distance. This simple principle has allowed us to map the universe in 3 dimensions, revealing a sprawling web of galaxies stretching billions of light years across. And hidden in that map are clues to everything from the birth of the first stars to the mysterious force we call dark energy, which seems to be pushing the universe apart faster and faster. What's even wilder is how redshift lets us time travel. When we look at a galaxy with high redshift, we're not just seeing it as it is today, we're seeing it as it was when its light began its journey, sometimes billions of years ago. A galaxy with a redshift of 1, for example, shows us the universe when it was half its current age. Go higher, and we're peering into an era when galaxies were still clumping together, their stars just beginning to ignite. It's like flipping through a photo album of the cosmos, each page revealing a younger, more chaotic universe. And the deeper we look, the more we realize how much we still don't understand. Some galaxies have redshift so extreme their light has been stretched nearly into invisibility, pushing our telescopes to their limits. Yet every time we break through those barriers, we uncover new pieces of the puzzle, proof that the universe's story is far stranger than we ever imagined. Picture a cosmic nursery where newborn stars ignite in brilliant bursts of blue. This is what a young galaxy looks like. The vibrant blue hue isn't just for show. It's the signature of massive, hot stars burning furiously and dying young, like fireworks lighting up the darkness. These stars dominate a galaxy's color palette early in its life, painting it in shades of sapphire and cyan. But time changes everything. As millions of years pass, those bright blue stars explode in supernova or fade away, leaving behind smaller, cooler stars that glow with a reddish tint, like embers in a cosmic campfire. This shift from blue to red is more than just a visual change. It's a timeline of a galaxy's life written in light. Now, imagine stumbling upon a galaxy that defies this rule, one that glows an unexpected shade of green or violet. These oddballs aren't just cosmic accidents, they're clues to something extraordinary. A galaxy tinged with green might be caught in the act of merging with another, its gas and stars stirred up like paint in a swirling vortex. Others might show patches of intense blue amid a sea of red, hinting at sudden bursts of star formation triggered by a close encounter with a neighbor. And then there are the quasars, galaxies with supermassive black holes at their cores whose furious energy can overpower the light of every star around them, skewing the color in ways that baffled astronomers for decades. The real magic happens when scientists compare galaxies across the universe. By cataloging their colors, they've uncovered a surprising pattern. The farther back in time they look, the bluer the universe appears. It's as if the early cosmos was a bustling factory of star birth, while today's universe is quieter, its galaxies aging into reddish retirement. But even this trend has its exceptions. Some ancient galaxies, spotted in the deepest reaches of space, are unexpectedly red, raising questions about how the first galaxies formed so quickly, or whether our telescopes are missing pieces of the puzzle. Every color tells a story, and sometimes the most fascinating chapters are the ones that don't fit the script. What's truly remarkable is how much we can learn from something as simple as color. A galaxy's hue reveals not just its age, but its diet, what kinds of gases it's consuming to fuel new stars, and even its destiny. Blue galaxies, rich with gas, are cosmic engines of creation, while red ones, their fuel spent, are like graveyards of ancient stars. And when two galaxies collide, their colors can mix in unpredictable ways, offering a front-row seat to the chaotic dance of cosmic evolution. This isn't just astronomy, it's detective work on the grandest scale, where every shade of light is a clue waiting to be decoded. But here's the twist: sometimes a galaxy's colors aren't just about the stars themselves. Imagine walking through a dense fog at sunset. The light dims, the colors soften, and everything takes on a hazy glow. That's exactly what happens in space, but instead of fog, it's vast clouds of dust and gas drifting between the stars. These interstellar particles don't just sit there, they actively sculpt the light passing through them, bending and filtering it like a cosmic stained glass window. A galaxy that might have blazed blue in its youth can appear mysteriously reddened because its dust is soaking up that energetic blue light, leaving only the warmer tones to reach us. And it's not just about dimming the view. Dust has a way of revealing secrets we'd otherwise miss. Take infrared light, for example. While our eyes can't see it, telescopes like the James Webb Space Telescope can peer straight through those dusty veils, uncovering galaxies that would have been invisible in ordinary light. Some of the most active star-forming galaxies are actually hiding behind thick curtains of dust, their newborn stars blazing in infrared like hidden bonfires. Without accounting for these dusty disguises, astronomers might mistake a galaxy's true nature, thinking it's old and quiet when it's actually a stellar nursery in disguise. The real breakthrough comes when scientists learn to subtract these dusty effects. By studying how different wavelengths interact with dust and gas, they can reverse engineer a galaxy's original colors, like cleaning an ancient painting to reveal its vibrant hues beneath centuries of grime. This process has led to some astonishing discoveries, like galaxies that appeared ordinary in visible light, but turned out to be monstrously bright once their dust was accounted for. It's a reminder that the universe loves playing tricks on us, hiding its most spectacular sights just out of plain view. But dust isn't just an obstacle, it's also a storyteller. The very presence of certain dust grains can hint at a galaxy's history, like finding footprints in snow. Some galaxies are dust-rich because they've been devouring smaller neighbors, swallowing up their gas and debris. Others might show patchy dust patterns, evidence of titanic explosions from dying stars that scattered material like cosmic shrapnel. And in rare cases, the dust itself glows in unexpected colors, heated by hidden black holes or shockwaves from colliding gas clouds. Every speck of dust, it turns out, has its own tale to tell. What makes this puzzle so thrilling is how dynamic it all is. Dust doesn't just sit there, it moves, clumps, and evolves over time, constantly reshaping how we see the galaxies around us. A single dust cloud might obscure a brilliant blue star cluster today, only to be blown away by stellar winds tomorrow, revealing the galaxy's true colors like curtains parting on a stage. And as telescopes grow more powerful, we're catching these transformations in real time, watching as the universe paints and repaints its masterpiece right before our eyes. So the next time you see a reddish galaxy, remember, its color might not just be about age or distance. It could be whispering secrets about the invisible forces shaping it from within. The real magic of a galaxy's color lies in its stars, not as a uniform crowd, but as generations of individuals, each burning with its own fiery personality. Picture a cosmic metropolis where the brightest skyscrapers are massive blue stars, blazing with such intensity they could outshine a million suns. But their brilliance comes at a cost. These stellar giants burn through their fuel in just a few million years, ending their lives in spectacular supernova. Their light dominates a galaxy's color early on, painting it in vivid blues and ultraviolet hues. Yet for every blue giant, there are countless smaller, cooler stars, red dwarfs that smolder gently for hundreds of billions of years, outliving even the galaxy itself. It's this delicate balance between the short-lived blue stars and the enduring red ones that gives each galaxy its unique shade, like a painter mixing colors on a cosmic palette. But stellar populations aren't just about aesthetics, they're forensic evidence. Astronomers can peer at a galaxy's color and instantly gauge its star-forming history. A galaxy rich in blue light is like a bustling factory floor, where new stars are constantly being forged from clouds of gas and dust. Over time, as those blue stars explode or fade, the galaxy's color shifts toward red, signaling a quieter era where star formation slows to a trickle. This transition isn't just inevitable, it's a clock ticking in deep space, revealing how long ago a galaxy's most active period occurred. Some galaxies, like our Milky Way, are in their middle ages, still birthing new stars but with a growing population of older, redder suns. Others, especially in dense galaxy clusters, have aged into red senility, their star-forming gas stripped away by collisions or superheated plasma. Then there are the cosmic anomalies, galaxies that defy the rules. Imagine finding a seemingly ancient, reddish galaxy suddenly bursting with patches of blue. At first glance, it makes no sense, but dig deeper, and the story unfolds. Perhaps it collided with a gas-rich neighbor, reigniting star formation in a late-life renaissance. Or maybe it cannibalized a smaller galaxy, swallowing fresh fuel to birth a new generation of stars. These rejuvenated galaxies are like retirees suddenly running marathons, challenging our assumptions about how galaxies evolve. Even more puzzling are the Green Valley galaxies, neither blue nor fully red, caught in a transitional phase that hints at unknown forces shutting down star formation faster than models predict. The key to decoding these mysteries lies in spectroscopy, where astronomers split a galaxy's light into its individual wavelengths like a cosmic barcode. Hidden in those spectral lines are the fingerprints of elements forged in stellar cores: oxygen from blue supergiants, iron from ancient red giants, even traces of carbon from dying stars. By reading these signatures, scientists can reconstruct a galaxy's life story with astonishing precision, like archaeologists sifting through layers of cosmic sediment. Some galaxies reveal multiple generations of stars superimposed, their colors blending like strata in a canyon wall. Others show abrupt changes, evidence of violent mergers or internal upheavals that reshaped their destiny. What's truly humbling is how these stellar populations connect to the universe's grand narrative. The earliest galaxies were likely dominated by blue stars, their light filtering through pristine clouds of hydrogen. Over eons, as successive generations of stars enriched the cosmos with heavier elements, galaxies grew redder and more complex. Yet even now, new puzzles emerge like ultra-distant galaxies that appear redder than they should, hinting at unknown processes in the infant universe. Every color shift, every stellar population is a piece of a puzzle spanning billions of years. And as telescopes grow more powerful, we're not just observing these stories, we're learning to read them in their original language, written in starlight. At the heart of many galaxies lies a cosmic powerhouse so intense, it can rewrite the rules of color entirely, a supermassive black hole. But these aren't the silent, lurking voids you might imagine. When a black hole feeds, it doesn't just swallow matter quietly. It throws a tantrum of cosmic proportions, heating infalling gas to millions of degrees until it glows with enough energy to outshine every star in its host galaxy combined. This frenzy, called an active galactic nucleus, doesn't just add light, it warps a galaxy's entire color signature, like a spotlight drowning out the subtler hues of a stage. Take the quasar, for example, a galaxy so dominated by its ravenous black hole that the core alone can appear 1,000 times brighter than the Milky Way. To the untrained eye, it might just look like an unusually bright star, but dissect its light and the truth emerges. A blaze of ultraviolet and X-rays, far beyond what normal stars produce, skewing the galaxy's color toward the blue end of the spectrum. Yet that's not the only trick these monsters have. Some active galaxies, shrouded in thick dust, beam their energy outward in infrared, glowing red-hot like embers hidden beneath cosmic soot. Others send jets of particles racing at near light speed, stirring up surrounding gas until it fluoresces in eerie greens and yellows. What makes these color shifts so valuable to astronomers isn't just their spectacle, it's their specificity. The exact blend of wavelengths emitted by an active nucleus acts like a fingerprint, revealing the black hole's diet, spin, and even how it's oriented relative to Earth. A galaxy that might have appeared red and aging could suddenly betray its true nature when X-rays pierce through, exposing a voracious black hole beneath. And sometimes the opposite happens. What looks like a blue, star-forming galaxy might actually owe its hue to a hidden monster, its radiation mimicking the light of newborn stars. The real breakthrough came when astronomers realized these active nuclei aren't just outliers, they're phases nearly every galaxy goes through. Picture a supermassive black hole as a sleeping giant, occasionally waking to feast on a passing gas cloud or a hapless star. Each feeding frenzy leaves behind a color echo, a temporary stain on the galaxy's light that fades over millennia. By cataloging these signatures, scientists have pieced together a hidden timeline of galactic adolescence, where violent black hole outbursts may actually stunt star formation, turning blue galaxies red long before their time. But here's the twist: sometimes the black hole's influence is subtler. In galaxies like our own Milky Way, where the central black hole is relatively quiet, its faint X-ray glow still tweaks the overall color, like a drop of dye in a clear pool. And in rare cases, two galaxies merging can funnel so much gas toward their black holes that both ignite simultaneously, creating a kaleidoscope of conflicting colors that baffled astronomers until they recognized the double act. The deeper we look, the clearer it becomes. Black holes aren't just residents of galaxies. They're sculptors, shaping their hosts' colors, evolution, and even their ultimate fates. And with tools like the James Webb Space Telescope now peering through dust and time, we're catching these cosmic transformations in action, watching as a galaxy's color flickers and shifts under the influence of its hidden heart. It's a reminder that in the universe's grand gallery, even the most vibrant hues often have the darkest origins. Some galaxies refuse to fit neatly into our cosmic color wheel, like those rare, enigmatic ones that glow with an unmistakable green tint. Unlike the fiery reds or vibrant blues of their neighbors, these green galaxies occupy a mysterious middle ground, as if the universe hit pause during their transformation. Picture a forest at twilight, not quite day, not quite night, and you'll understand why astronomers find these objects so fascinating. They're cosmic liminal spaces, caught between phases of stellar birth and quiet aging, offering clues to processes we're only beginning to unravel. What makes a galaxy green? It's not as simple as mixing starlight like paint. While blue galaxies blaze with young stars and red ones smolder with aging giants, green galaxies often signal a delicate balancing act. Some might be slowing their star formation, their blue stars fading while red giants haven't yet taken over. Others could be the product of galactic mergers, two galaxies colliding and stirring their stellar populations like ingredients in a cosmic blender. When gas-rich galaxies combine, the resulting chaos can trigger bursts of star formation while also heating dust to glow in infrared, blending blue and red light into eerie green hues. Then there's the chemistry angle. Certain elements, like ionized oxygen, emit light at specific green wavelengths when energized by newborn stars or black hole activity. In some green galaxies, these emissions dominate, painting the entire system in a surreal emerald glow. It's as if the galaxy is sending out a beacon in a color most others can't replicate. But here's the puzzle. Many green galaxies don't fit these explanations neatly. Some show no signs of mergers or extreme chemistry, leaving astronomers scratching their heads. Could they be experiencing a sudden shutdown of star formation, stranding them in chromatic limbo? Or are we seeing the aftermath of a galactic-scale event, like a black hole's outburst altering the galaxy's light in ways we don't yet understand? The most intriguing green galaxies are those found in the early universe, spotted by telescopes like Hubble and James Webb. These ancient objects shouldn't exist under standard models. They're too massive, too evolved for their time, yet there they glow, green and defiant. Their very existence hints at gaps in our understanding of how quickly galaxies matured after the Big Bang. It's like finding a fully grown tree in what should be a field of saplings. Some theorists suggest these outliers might be the first generation of galaxies transitioning from star-forming powerhouses to quieter states, caught in a fleeting phase that most galaxies passed through long ago. What makes these green mysteries so valuable isn't just their rarity, it's their defiance of categories. In science, we love tidy classifications, but the universe keeps reminding us that reality is messier. A green galaxy might be a teenage giant growing too fast, a cosmic collision frozen in time, or something entirely unexpected. Every new discovery in this niche, like the recent green pea galaxies, small but glowing intensely with oxygen, challenges our textbooks. They're proof that the universe still holds chromatic secrets, waiting for the next generation of telescopes and curious minds to decode them. Human eyes are incredible tools, but they're limited, like trying to understand an entire symphony by hearing only a few notes. The visible light we see is just a sliver of the vast electromagnetic spectrum, and galaxies pour out stories in wavelengths our eyes will never perceive. That's where telescopes like Hubble and James Webb become our cosmic translators, revealing the universe's hidden vocabulary in infrared and ultraviolet light. These invisible colors don't just fill in gaps, they rewrite entire chapters of what we thought we knew about galaxies. Take infrared light, for example. While our eyes see darkness, infrared telescopes unveil galaxies shrouded in dust. their star-forming regions glowing like hidden embers. Picture a cosmic construction site where thick clouds of dust obscure newborn stars in visible light, but switch to infrared, and suddenly those clouds become nearly transparent, revealing stellar nurseries blazing with activity. This is how the James Webb Space Telescope has spotted some of the earliest galaxies in the universe, their light stretched into infrared by the expansion of space itself. Without this window, we'd miss entire generations of galaxies, their existence erased by the very dust that helped create them. Then there's ultraviolet light, the domain of the hottest, most massive stars. These stellar behemoths burn so fiercely they emit most of their energy in ultraviolet, painting their host galaxies in colors invisible to our eyes. To a telescope like Hubble's ultraviolet-sensitive instruments, a seemingly ordinary galaxy can transform into a riot of activity, with young star clusters blazing like fireworks. But ultraviolet isn't just about youth, it's also a tracer of violence. When galaxies collide, the shockwaves compress gas, triggering bursts of star formation that flood the system with ultraviolet light. And in quasars, the ultraviolet glare from supermassive black holes outshines everything else, exposing the furious energy at a galaxy's core. What's truly revolutionary is how these wavelengths work together. A galaxy that appears red and aging in visible light might reveal a different story in ultraviolet patches of star formation hidden beneath layers of dust, or a central black hole pumping out high-energy radiation. Meanwhile, infrared can expose the heat from that same dust, mapping structures invisible in other wavelengths. It's like assembling a puzzle where each piece shows a different layer of the galaxy's life. Some galaxies even appear radically different depending on the light you use. A faint smudge invisible becomes a sprawling monster in infrared, or a quiet red giant in optical transforms into an ultraviolet powerhouse. The implications go far beyond pretty pictures. By combining these wavelengths, astronomers have discovered galaxies that defy classification, objects so dusty they're practically invisible in optical light, yet brilliant in infrared, or ancient galaxies still forming stars at rates that shouldn't be possible. These outliers challenge our models of galactic evolution, forcing us to ask, have we been missing entire populations of galaxies simply because we weren't looking in the right light? Perhaps the most profound revelation is how much remains hidden. For every galaxy we've studied in multiple wavelengths, there are countless others we've only glimpsed in one. New telescopes promise to peel back even more layers, from far infrared observatories probing the coldest dust to X-ray telescopes tracing the aftermath of stellar explosions. Each new window reveals another piece of the galaxy's secret language, proving that to truly understand the cosmos, we can't just rely on what our eyes can see. We have to listen to the full spectrum of its light. Galaxies don't exist in isolation, they're part of vast cosmic communities, and just like neighborhoods on Earth, these environments shape their destiny. Picture a bustling city center compared to a quiet countryside. Galaxies in dense clusters live fast and die young, their vibrant blue hues fading to red as their star-forming gas is stripped away. This process, called environmental quenching, is one of the universe's most dramatic makeovers. It starts when a galaxy falls into a crowded cluster, where superheated gas between galaxies acts like a cosmic blowtorch, evaporating the cool hydrogen needed to birth new stars. Without fresh fuel, the galaxy's blue giants burn out, leaving behind older, redder stars and a color signature that tells astronomers exactly what happened. But it's not just hot gas that reshapes these galaxies. Imagine a crowded dance floor where partners keep swapping. That's what happens in galaxy clusters. Close encounters between galaxies can wrench away their gas or trigger bursts of star formation that exhaust their reserves prematurely. Some galaxies are even torn apart entirely, their stars scattered into the cluster's halo-like glitter in the wind. These violent interactions leave behind red and dead elliptical galaxies, smooth and featureless compared to their spiral counterparts, the strangest part. This transformation can happen shockingly fast within a billion years. A galaxy can go from blue and star-forming to red and retired, all because of where it lives. The fingerprints of this process are everywhere. In the Virgo cluster, our nearest galactic city, astronomers see galaxies at every stage of quenching, some still clinging to their blue star-forming regions, others already fully red. The Coma cluster, farther away, is like a galactic retirement home, packed with ancient red galaxies that haven't formed new stars for eons. Even more telling are the Green Valley galaxies caught in between, their colors hinting at recent quenching. By mapping these color patterns across clusters, scientists have uncovered a universal rule: the denser the environment, the redder the galaxies. It's as if the universe has a recipe for aging galaxies, and crowded clusters follow it perfectly. Yet mysteries remain. Some galaxies in clusters stubbornly cling to their blue hues, defying the quenching trend. These rebels often orbit the cluster's outskirts, where conditions are milder, or harbor unusually strong magnetic fields that shield their gas. Others might be recent arrivals, still holding onto their star-forming fuel like travelers with a full canteen in the desert. And in the most massive clusters, astronomers have spotted blue blobs, pockets of gas where star formation somehow reignites like oases in a cosmic wasteland. These exceptions prove that while environment is powerful, it's not the whole story. What's truly groundbreaking is how these color shifts reveal the universe's large-scale structure. By studying red galaxies in distant clusters, astronomers can trace how quenching evolved over cosmic time. Early clusters, seen as they were billions of years ago, show more blue galaxies, proof that environmental quenching took time to dominate. Some superclusters, the universe's largest structures, even display gradients of color, with galaxies growing redder toward the crowded center. It's a pattern that repeats across the cosmos, linking the fate of individual galaxies to the vast web of matter they're embedded in. The lesson is clear: a galaxy's color isn't just about what's inside it, it's about where it lives. Just as people are shaped by their communities, galaxies are products of their environments, their hues telling stories of cosmic eviction, violent encounters, and slow starvation. And as telescopes peer deeper into the universe's densest neighborhoods, they're uncovering the precise moments when galaxies lose their blue, painting a picture of cosmic evolution written in color. Every time we gaze at a distant galaxy, we're not just looking across space, we're peering back through time. Light travels fast, but the universe is so vast that even at light speed, it takes millions or billions of years to reach us. That means the light from the farthest galaxies shows us what they looked like when the universe was young, like flipping through an ancient photo album where each page reveals an earlier chapter of cosmic history. And the colors in these snapshots aren't just pretty, they're vital clues to how galaxies grow and change. Those remote, blue-tinted galaxies are like cosmic toddlers, bursting with energy and new stars. In the early universe, galaxies were smaller, gas-rich, and furiously forming stars at rates that would put our Milky Way to shame. Their blue hue comes from countless massive, short-lived stars blazing with intense heat, stellar giants that burned bright and died young. But as the universe aged, galaxies transformed. Star formation slowed, those blue stars faded, and older, redder stars began to dominate. It's a pattern we see echoed across the cosmos. The farther back in time we look, the bluer and more active galaxies appear, while nearby galaxies tend to be redder and more settled. This cosmic time machine isn't just about spotting differences, it's about understanding why they happen. By comparing galaxies from different eras, astronomers have pieced together a timeline of galactic evolution. Young galaxies were chaotic, colliding and merging frequently, their gas reservoirs constantly replenished. Over billions of years, as the universe expanded and gas became scarcer, star formation dwindled. Some galaxies exhausted their fuel entirely, leaving them red and dead, while others, like our Milky Way, found a slower, steadier rhythm. The real breakthrough came when telescopes like Hubble and James Webb began spotting ultra-distant galaxies with surprising colors, some redder than expected, hinting at unknown processes in the early universe. These outliers challenge our theories, suggesting that galaxies could mature faster than we thought, or that hidden forces like supermassive black holes played a bigger role in shaping their evolution. Each new observation adds another piece to the puzzle, revealing how galaxies transition from blue youth to red old age. What's truly astonishing is how much detail we can extract from these ancient light beams. By measuring subtle color shifts, astronomers can estimate a galaxy's distance, age, and even its chemical composition. A faint blue smudge in a telescope might turn out to be a galaxy as it appeared just 500 million years after the Big Bang, its light carrying the signatures of the first heavy elements forged in stars. Others might show unexpected greens or yellows, hinting at turbulent periods when galaxies collided or black holes erupted. This isn't just astronomy, it's time travel, letting us watch the universe grow up in real time. Every galaxy's color is a timestamp, a clue to what the cosmos was like when that light began its journey. And as telescopes probe ever deeper into space and further back in time, we're catching glimpses of the universe's first chapters, written in starlight. The James Webb Space Telescope isn't just another instrument, it's a revolution in how we see the universe. Unlike Hubble, which primarily observes visible and ultraviolet light, Webb specializes in infrared, a wavelength range that lets it cut through cosmic dust like a heat sensor piercing fog. This capability is transforming our understanding of galactic colors, revealing details hidden since the dawn of time. Take those stunning early images of galaxy cluster SMACS 0723. What looked like faint smudges in older telescopes exploded into intricate structures under Webb's gaze, their colors telling stories of star formation and chemical enrichment we'd never glimpsed before. But the real shock came when Webb started spotting galaxies that shouldn't exist, at least, not according to our old models. These ancient galaxies, seen as they were just a few 100 million years after the Big Bang, glow with a maturity that defies expectations. Some show surprisingly red hues, suggesting they'd already formed vast numbers of stars and heavy elements far earlier than anyone predicted. Others display bizarre color combinations, like blue cores wreathed in red dust, hinting at violent bursts of star formation or black hole activity in the universe's infancy. These aren't just incremental discoveries, they're forcing astronomers to rethink how quickly galaxies could evolve. Webb's secret weapon is its ability to dissect light with exquisite precision. Every galaxy's infrared spectrum is like a barcode, encoding information about its stars, gas, and dust. By reading these patterns, scientists can measure exact redshifts, even for galaxies so distant their light has been stretched nearly beyond recognition. This precision has already solved mysteries, like the case of a peculiarly red galaxy once thought to be extremely old. Webb revealed its color wasn't from age but from thick dust, a finding that upended assumptions about how early galaxies enriched their environments. Perhaps the most thrilling aspect is how Webb catches galaxies in transition. In the early universe, where Hubble saw mostly blue star-forming systems, Webb is spotting galaxies mid-quenching, their colors shifting as they exhaust their gas. Some show greenish tints, a sign they're straddling the line between youth and retirement. Others flicker with unexpected ultraviolet, betraying hidden black holes or shock waves from cosmic collisions. Each observation adds a new verse to the color-coded narrative of galactic evolution. What makes Webb truly groundbreaking is its capacity to connect these dots across time. By comparing galaxies from different epochs from the cosmic dawn to the present, we're seeing the full story of how blue, star-filled youngsters mature into red, aging giants. And with every unexpected color it uncovers, Webb reminds us that the universe's palette is far richer and more mysterious than we ever imagined. This isn't just astronomy. It's like decoding a cosmic Rosetta Stone, one infrared photon at a time. Imagine trying to read a library where every book is written in faint, shifting colors. That's the challenge astronomers face with today's flood of galactic data. Modern telescopes like the Vera Rubin Observatory capture millions of galaxy images nightly, far more than humans could ever analyze manually. That's where machine learning steps in, acting as a cosmic Rosetta Stone to decode the subtle language of galactic colors. These algorithms don't just classify galaxies as red or blue. They detect gradients and patterns invisible to the human eye, spotting outliers that might hold clues to black hole activity, rare star formation events, or even unknown physical processes. The magic lies in how these systems learn. By training on thousands of galaxies with known properties like age, distance, and chemical composition, machine learning models begin to connect the dots between color and underlying physics. A slight greenish tint in one galaxy might signal a specific mix of ionized gases, while an unusual ultraviolet glow in another could betray the presence of a hidden black hole. Some algorithms go further, simulating entire galactic life cycles to predict how a young blue spiral might evolve into a red elliptical over billions of years. It's like watching time-lapse footage of a flower blooming, but for galaxies. What's truly groundbreaking is how these tools handle ambiguity. Human astronomers might dismiss a galaxy as weirdly colored and move on, but machine learning digs deeper. In one recent study, an AI flagged a group of galaxies with anomalous yellow hues. Turns out, they were caught in a rare phase of simultaneously forming and quenching stars, a phenomenon previously thought impossible. Other models have identified cosmic chameleons, galaxies whose colors change dramatically depending on viewing angle, revealing how dust clouds distort our perspective. The future is even more exciting. Next-generation AI promises to reconstruct galactic histories from single snapshots, like forensic scientists piecing together a crime scene. Imagine feeding a telescope image into a model and receiving not just the galaxy's current state, but a play-by-play of its past collisions, starbursts, and black hole eruptions. Some teams are already using generative AI to simulate how the Milky Way might look in 5 billion years, its colors shifting as it collides with Andromeda. Others train algorithms on hypothetical galaxies to explore what-if scenarios, like how cosmic rays or dark matter might influence color over time, but the real game changer. These tools are starting to find patterns no human ever predicted. When an AI system recently clustered galaxies by color in a way that defied traditional classifications, astronomers discovered a new dimension to galactic aging, one tied not just to stars, but to the invisible halos of dark matter surrounding them. It's a reminder that the universe's color code is far more complex than we imagined. And with machine learning as our guide, we're just beginning to crack it. Galactic collisions are the ultimate cosmic makeovers, violent, beautiful, and utterly transformative. Picture two spiral galaxies, each with billions of stars, drifting closer over millions of years until gravity pulls them into a gravitational tango. At first, their colors might seem unchanged: blue arms tinged with young stars, reddish cores glowing with older ones, but as they merge, all hell breaks loose. Gas clouds slam together, compressing under unimaginable pressure until they ignite in a firestorm of new star birth. Suddenly, what was once a sedate galaxy erupts in blue-hot brilliance, its color shifting like a chameleon on a sunlit leaf. Astronomers call these starburst galaxies, and they are some of the most luminous objects in the universe, blazing with the light of millions of newborn stars. But starbursts are just the opening act. As the merger progresses, those blue stars, massive and short-lived, explode in supernova or fade away, leaving behind smaller, redder stars. The galaxy's color gradually cools from blue to white, then yellow, and finally red, like a piece of metal cooling from molten heat. This transition isn't smooth. It's chaotic, with pockets of blue persisting where gas remains, while other regions redden prematurely. The end result, a galaxy that might have started as a delicate spiral, emerges from the collision as a featureless elliptical, its colors telling the story of a violent past. The real magic lies in the details. Take the antennae galaxies, one of the most famous merging pairs. In visible light, they're a riot of blue star clusters and pinkish gas clouds, the hallmark of intense star formation. But switch to infrared, and another layer appears: thick dust lanes glowing with the heat of hidden stellar nurseries. This multi-wavelength view reveals how mergers don't just change a galaxy's color. They scramble it, mixing populations of stars and dust in ways that can baffle astronomers. Some merged galaxies even exhibit green valley colors, caught between the blue of youth and the red of old age, as if the universe hit pause during their transformation. What's truly astonishing is how long these color shifts endure. Long after the merger is complete, the galaxy's hue remains a fossil record of the collision. Ancient elliptical galaxies, now red and dead, often show chemical signatures proving they were once spirals that merged billions of years ago. Their colors are like cosmic scars, hinting at a turbulent youth we can only reconstruct through simulations and forensic astronomy. And then there are the outliers, galaxies that defy expectations. Some mergers, rather than triggering star formation, seem to quench it almost immediately, their gas stripped away or heated too quickly to form stars. These galaxies skip the blue phase entirely, turning red faster than models predict. Others, like the rare blue ellipticals, somehow retain their star-forming gas despite merging, challenging our assumptions about how these encounters unfold. Every collision is a laboratory for the extremes of physics, a chance to watch galaxies evolve in fast forward. By studying their colors before, during, and after mergers, astronomers are piecing together a universal recipe for galactic evolution, one where violence and beauty are inextricably linked. The next time you see a red elliptical galaxy, remember, its color isn't just a shade. It's a story of catastrophe, rebirth, and the endless dance of the cosmos. Quasars are the universe's ultimate overachievers, cosmic beacons so bright they can drown out the combined light of every star in their host galaxies. At their cores, supermassive black holes gorge on surrounding matter, heating it to millions of degrees until it glows with enough energy to outshine entire galactic neighborhoods. But what makes quasars truly fascinating isn't just their brilliance, it's how they warp the very colors we use to study galaxies. Like a spotlight pointed at a painting, their intense radiation can completely reshape a galaxy's spectral signature, turning what should be a balanced mix of starlight into a dazzling, blue-dominated spectacle. The secret lies in the accretion disk, a swirling maelstrom of gas and dust spiraling into the black hole at nearly light speed. Friction heats this material until it emits torrents of ultraviolet and X-ray radiation, far beyond what normal stars produce. To telescopes, this creates a glaring mismatch. While the galaxy's stars might collectively glow with a reddish hue typical of older stellar populations, the quasar's piercing blue-white glare overwhelms everything, skewing the entire system's color toward the high-energy end of the spectrum. It's as if someone took a cosmic paintbrush and splashed electric blue across a somber red canvas. But quasars don't just mask their host galaxies, they transform them. Their radiation can ionize surrounding gas, stripping electrons from atoms and preventing new stars from forming. Over time, this process called quasar feedback can turn a vibrant, star-forming galaxy into a red and dead relic, its color shifting from blue to red as star birth grinds to a halt. In some cases, quasars even blast away their host galaxy's gas entirely, creating bizarre hybrids where a brilliant blue core sits surrounded by a faint, reddened fringe of aging stars. The most extreme examples defy logic. Take the quasar SDSS J0100 plus 2802. Its host galaxy appears utterly unremarkable in visible light, but ultraviolet observations reveal a monster black hole emitting enough high-energy radiation to power 1,000 Milky Ways. Then there's the red quasar phenomenon, rare objects shrouded in so much dust that their blue and ultraviolet light gets absorbed, re-emitted as infrared, giving them a deceptively cool, reddish appearance. These cosmic chameleons remind us that appearances can be deceiving, especially when black holes are involved. What's revolutionary is how quasars serve as time capsules. Because their light takes billions of years to reach us, high redshift quasars show us the early universe's most violent epochs. Some ancient quasars already had fully formed black holes weighing billions of suns, a puzzle for theorists, since there shouldn't have been enough time for such behemoths to grow. Their very existence hints at unknown processes in the cosmic dawn, where black holes and galaxies co-evolved in ways we're only beginning to decipher. By studying quasars across cosmic time, astronomers have uncovered a startling pattern. The most luminous quasars seem to peak when the universe was about 3 billion years old, then gradually fade. This matches the decline in average galactic star formation, suggesting a profound link between black hole activity and galaxy evolution. It's as if quasars were the universe's way of pressing pause on star birth, their fiery outbursts shaping the color and destiny of galaxies for eons to come. The next time you see a galaxy catalogued as blue, look closer. It might not be young stars you're seeing, but a hidden quasar rewriting the rules of cosmic color. These brilliant anomalies are more than just black hole fireworks. They're proof that the universe's most dramatic transformations often begin in the darkest places imaginable. The universe is slowly turning down the lights, not with a sudden flick of a switch, but with a gradual, inevitable fade that will stretch across billions of years. Imagine looking up at the night sky 1 trillion years from now. Where we see a tapestry of galaxies, future civilizations might peer into a far emptier cosmos, where even the brightest galactic neighbors have dimmed into near invisibility. This isn't science fiction. It's the unavoidable consequence of cosmic expansion, a process called the Great Dimming, where galaxies don't just move away from us, their light gets stretched, diluted, and fundamentally altered as space itself relentlessly grows. At the heart of this phenomenon is redshift pushed to its extreme. Just as a siren's pitch drops as it speeds away, light from distant galaxies stretches into longer, redder wavelengths as the universe expands. But over incomprehensible timescales, something stranger happens. The expansion accelerates thanks to dark energy until even nearby galaxies are carried away faster than their light can reach us. Their light doesn't just redden, it stretches into infrared, then microwaves, and eventually into radio waves so faint they're virtually undetectable. The most distant galaxies we see today will vanish first, their light stretched beyond recognition, followed by closer ones in a slow-motion disappearing act. What's eerie is how this dimming isn't uniform. Galaxies rich in young, blue stars will fade faster, their high-energy light more vulnerable to stretching. Older, redder galaxies might linger a bit longer, their cooler light less affected, but even they won't escape the inevitable. Over time, the universe's color palette will shift from vibrant blues and whites to deep reds, then to darkness. Astronomers call this the degenerate era, a time when star formation has ceased, black holes dominate, and the only visible light comes from rare, dying stars, a far cry from the starry spectacle we know today. Yet this cosmic dimming isn't just about loss, it's a key to understanding the universe's ultimate fate. By modeling how galaxies fade, scientists can test theories about dark energy's behavior, whether it will keep accelerating expansion indefinitely or mysteriously weaken. Some simulations suggest that in 100 billion years, only the Milky Way and its nearest galactic neighbors will remain visible, huddled together in an island of light amid an ocean of blackness. Others hint at even stranger possibilities, like distant galaxies freezing in time, their final photons arriving in stretched, ghostly whispers. The most profound lesson here is about cosmic perspective. We live in a privileged moment, a sliver of time when the universe is still bright enough to read its history in starlight. Future astronomers might never know galaxies existed beyond their local cluster, their telescopes blind to the evidence of the Big Bang or galactic evolution. It's a humbling reminder that the universe isn't static, it's a story unfolding, and we're lucky enough to witness a vivid chapter. So the next time you gaze at a galaxy swirling in the night sky, remember, you're not just seeing a distant object. You're catching a fleeting glimpse of a cosmos that won't always shine so brightly. Dark matter may be invisible, but its fingerprints are all over the colors we see in galaxies. Picture an unseen puppeteer pulling strings behind a cosmic stage. Dark matter's gravitational grip shapes where galaxies form, how they move, and ultimately how they evolve. While our telescopes can't directly spot this mysterious substance, its influence is written in the hues of galaxies, like hidden ink revealed under ultraviolet light. Take the striking difference between galaxies in crowded clusters and those drifting alone in cosmic voids. Cluster galaxies, swimming in dense pools of dark matter, often appear red and aging, their star-forming gas stripped away by violent encounters. Meanwhile, isolated galaxies in dark matter-poor regions tend to stay blue longer, their gas reservoirs untouched, birthing new stars in peace. The connection goes deeper than mere location. Dark matter doesn't just herd galaxies together, it sets the tempo for their entire life cycle. A galaxy cocooned in a massive dark matter halo, for instance, might funnel gas toward its center faster, igniting bursts of star formation that paint it blue before abruptly quenching it. Others with lighter halos could experience slower, steadier star birth, their colors shifting gradually from blue to red over eons. Even the bizarre, ultra-diffuse galaxies, which glow faintly despite their size, owe their ghostly appearance to dark matter. Some of these cosmic specters are nearly transparent, their stars scattered thinly across vast dark matter halos, while others are strangely rich in dark matter, their faint blue hues hinting at star formation defying expectations. What's truly groundbreaking is how astronomers use color to map the invisible. By analyzing the reds and blues of thousands of galaxies, researchers can reconstruct the hidden scaffolding of dark matter binding the universe together. For example, galaxies along the filaments of the cosmic web, where dark matter is densest, show distinct color patterns, aging faster than those in emptier regions. Some teams have even spotted color gradients within individual galaxies, with outer regions redder than their cores, betraying the shape and mass of their dark matter halos. It's like deducing the shape of a shadow by watching how light bends around it. The most tantalizing clues come from outliers. Certain galaxies, like the blue orphans, found far from any dark matter cluster, challenge our theories. How do they retain their star-forming gas without dark matter's protective pull? Others, like the red galaxies in seemingly empty voids, suggest dark matter might be distributed in ways we haven't yet imagined. Every anomaly forces us to rethink the relationship between the unseen and the visible, between the cosmos's hidden architecture and the palette of light it produces. This isn't just about solving a cosmic mystery, it's about rewriting galactic history. By reading the colors of galaxies as a code, we're uncovering dark matter's role in turning the early universe's blue star factories into the red giants we see today. And with every new observation, we're one step closer to answering the ultimate question. How much of a galaxy's story is written by the stars we see, and how much by the darkness we don't? Galactic archaeology doesn't require shovels or brushes, just telescopes and an eye for color. Every shade in a galaxy's spectrum is like a layer of sediment, preserving clues to its past. Take the Andromeda Galaxy, our nearest spiral neighbor. Its outer halo glows with a faint reddish hue, packed with ancient stars that formed over 10 billion years ago. But look closer, and you'll spot patches of blue clusters of younger stars that shouldn't be there. These aren't random, they're cosmic graffiti, evidence of smaller galaxies Andromeda cannibalized long ago, their stolen stars still burning bright against the older backdrop. The chemistry of light tells an even richer story. When astronomers split a galaxy's glow into its constituent wavelengths, they're not just seeing colors, they're reading the periodic table written in starlight. Heavy elements like iron and oxygen absorb specific wavelengths, creating dark lines in the spectrum like barcodes. Older stars, born when the universe was young and pristine, show thin lines, their metal poor, forged from little more than hydrogen and helium. Younger stars, by contrast, are metal-rich, their spectra crowded with absorption lines from elements cooked in earlier stellar generations. By mapping these chemical fingerprints across a galaxy, scientists can trace its growth like rings in a tree trunk, revealing epochs of star birth, quiet periods, and violent mergers. Some of the most dramatic chapters come from galaxies with broken color gradients. Normally, spiral galaxies transition smoothly from blue arms to reddish cores, reflecting their star-forming outskirts and aging centers. But certain galaxies, like the famous Sombrero, flip this pattern entirely, with red arms and a surprisingly blue core. This inversion is a smoking gun. It suggests a past collision so violent it flung the galaxy's gas inward, triggering a late-life burst of star formation at its heart. Other oddballs, like the blue nugget galaxies found in the early universe, pack all their star formation into tiny, hyperactive cores, their colors defying expectations of how young galaxies should look. The ultimate prize in galactic archaeology, finding fossil galaxies, remnants of the first star systems that merged to build modern giants like our Milky Way. Recently, the Gaia spacecraft spotted strange streams of stars orbiting our galaxy's outskirts, all moving together like a school of fish. Their distinct reddish color and metal pore composition mark them as relics of a dwarf galaxy swallowed billions of years ago. its stars now dissolving into the Milky Way's halo. Similar fossils lurk in other galaxies, their colors preserving secrets from an era when the cosmos was a chaotic construction site. What makes this science so powerful is its ability to turn static images into dynamic histories. A single snapshot of a galaxy, analyzed through the prism of color and chemistry, can reveal collisions from eons past, dormant black holes, or even the ghostly imprint of dark matter. It's a reminder that the universe doesn't just keep time, it wears its history in light, waiting for those who know how to read it. Before the first galaxies flickered to life, the universe was a vast, featureless void, a cosmic canvas waiting for its first brushstroke of color. Picture a time when space was filled with nothing but a thick fog of hydrogen gas, so dense it absorbed all light like a cosmic blindfold. Then, around 200 million years after the Big Bang, something extraordinary happened. The first stars ignited, their ultraviolet radiation cutting through the darkness like torches in a cavern, stripping electrons from hydrogen atoms in a process called reionization. This wasn't just the birth of light, it was the universe's first color show, painted in hues we're only beginning to decode. Those earliest galaxies didn't look anything like the spirals and ellipticals we see today. They were tiny, chaotic things, blazing with the blue-white fury of massive, short-lived stars. Without heavier elements to temper their nuclear furnaces, these stars burned at temperatures we'd consider impossible today, flooding the cosmos with ultraviolet light that turned the surrounding hydrogen from opaque to transparent. To our telescopes, this epoch appears as a subtle shift in color, a faint reddening of light that's traveled so far, it's been stretched by the expanding universe into infrared. It's like trying to hear a whisper across a roaring stadium, but for astronomers, that whisper holds the secrets of cosmic infancy. The James Webb Space Telescope is our best ear for those whispers. Its infrared eyes can peer back to when the universe was less than 5% its current age, spotting galaxies so young their light hasn't yet been fully redshifted into invisibility. Some of Webb's earliest targets showed something shocking: galaxies that were too red, too mature for their age. Instead of the expected blue blobs of newborn stars, these ancient systems glowed with hints of orange and crimson, evidence of rapid star formation and dust production that defies our models. It's as if we opened a textbook on human evolution and found a toddler with gray hair. But the real treasure lies in the gaps between the first stars and the galaxy's Webb has spotted. There's a missing chapter, a period when the universe transitioned from darkness to light. Future telescopes, like the planned Nancy Grace Roman Space Telescope, aim to fill that gap by detecting the faint, diffuse glow of hydrogen as it was ionized. This cosmic dawn light wouldn't come from individual galaxies, but from the space between them, a faint pinkish hue created by the interplay of ultraviolet radiation and hydrogen gas. Capturing it would be like finding the first frame of the universe's home movie. What's at stake isn't just a timeline. The colors of these primordial galaxies encode the physics of the early universe, how quickly stars formed, how black holes grew, even the nature of dark matter. Some theories suggest the first galaxies should have a distinct greenish tint, a signature of their unique chemistry. Others predict entire populations of galaxies invisible to conventional telescopes, their light smothered by thick hydrogen fog. Every new observation forces us to rewrite the rules, revealing a cosmos far wilder in its youth than we ever dreamed, the most thrilling possibility. That we'll find colors with no modern counterpart, hues born from conditions so extreme they vanished billions of years ago. These wouldn't just be historical curiosities, they'd be clues to physics operating at energies we can't replicate on Earth. It's a reminder that the universe's first palette wasn't just a starting point, it was a laboratory of the impossible, waiting to be rediscovered. Imagine a vast cosmic puzzle with billions of pieces, each one a galaxy waiting to be catalogued. Now picture thousands of everyday people around the world, from students to retirees, coming together to solve it. That's the magic of Galaxy Zoo, a groundbreaking project that turns anyone with curiosity and an internet connection into a galactic detective. Since 2007, over 1 million volunteers have sifted through telescope images, classifying galaxies by their colors and shapes, work so intricate that even the most advanced algorithms struggle to match human intuition. What makes these citizen scientists so invaluable? It's their ability to spot the cosmic oddballs, the galaxies that don't fit the mold. Take Hannes Voorwerp, a glowing green cloud of gas discovered by Dutch schoolteacher Hanny van Arkel. Professional astronomers had scanned the same data for years, but it took a fresh pair of eyes to notice this bizarre object, now known to be illuminated by a quasar's long-dead light. Then there's the blue jellyfish galaxies, their tendrils of star-forming gas identified by volunteers who flagged what machines dismissed as noise. These discoveries aren't just curiosities, they're keys to understanding how galaxies interact, age, and sometimes defy expectations. The process is beautifully simple. Participants view images from surveys like the Sloan Digital Sky Survey, then answer basic questions. Is the galaxy blue or red, spiral or elliptical? Smooth or clumpy, but beneath that simplicity lies profound science. Each classification helps build a map of galactic evolution, revealing how color correlates with shape, environment, and age. When thousands of people agree on a galaxy's hue, it creates data points robust enough to test theories about star formation, black holes, and dark matter. And when they disagree, those outliers often lead to breakthroughs like the rare red spiral galaxies that challenge assumptions about how galaxies transition from blue to red. What's truly revolutionary is how Galaxy Zoo blends human perception with machine learning. Volunteers' classifications train AI to recognize subtle patterns, creating a feedback loop where humans and algorithms grow smarter together. This synergy has uncovered entire new categories of galaxies, like the P's small, intensely green objects pumping out star-forming radiation. It's also revealed how biases creep into automated systems, where computers might misclassify a dusty red spiral as an elliptical. Humans notice the delicate arms hidden beneath the haze. Beyond the science, Galaxy Zoo taps into something deeper, our innate desire to explore. Every participant becomes part of a global community, sharing discoveries in forums and even co-authoring scientific papers. Teachers use it in classrooms, families bond over classifying galaxies together, and retirees find purpose in contributing to real research. In a world where professional astronomy often feels distant, Galaxy Zoo reminds us that the universe belongs to everyone, and that its colors, so full of secrets, are there for us all to decode. The next time you see a Hubble or Webb image, remember, some of its most fascinating details might have been spotted not by a telescope's lens, but by a curious person halfway across the world, proving that sometimes the best tool for deciphering the cosmos isn't technology, it's human wonder. Beyond the familiar blues and reds of typical galaxies lies a world of chromatic oddities, cosmic fireworks that defy every rule in the stellar color palette. Picture a galaxy that glows not with starlight, but with an eerie ultraviolet flare, as if someone had doused its core in invisible ink that only certain telescopes can see. These aren't artistic flourishes, they're screaming signatures of violence on a scale we're only beginning to comprehend. Take tidal disruption events, for instance, celestial cataclysms where a star wanders too close to a supermassive black hole and gets shredded into a glowing stream of plasma. The aftermath, a temporary burst of high-energy ultraviolet or even X-ray light that paints the host galaxy in surreal hues for months before fading, like a cosmic bruise revealing where the universe punched itself. Then there are the infrared rebels galaxies that emit 90% of their light in wavelengths far beyond what human eyes perceive. Peering into these cosmic furnaces with ordinary telescopes would show nothing remarkable, but switch to infrared, and suddenly they're blazing like signal flares. Some owe their glow to thick dust clouds heated by frenzied star formation, while others harbor something even stranger: supermassive black holes so deeply buried in dust that their radiation cooks the surrounding grains to infrared incandescence. The most extreme examples, dubbed hot DOGs, dust-obscured galaxies, are so luminous in infrared they outshine entire star clusters, their true brilliance hidden behind curtains of cosmic soot. But the real head-scratchers are the galaxies that flicker with polarized light, their photons aligned in specific directions, as if filtered through a cosmic lens. This rare phenomenon often betrays the presence of magnetized jets, where supermassive black holes launch particles at near light speed, twisting magnetic fields into helical coils that polarize the escaping light. It's like finding a galaxy wearing polarized sunglasses with the lenses made of pure space-time distortion. One such case, the Spanish Dancer Galaxy, spins jets so powerful they polarize light across thousands of light years, creating a celestial light show that's equal parts art and astrophysics. Perhaps the most tantalizing anomalies are the galaxies whose colors shift in ways no known matter can explain. Some exhibit patches of light that rotate inexplicably, as if vast, invisible hands were twisting their starlight like a dial. Others show spectral lines, the barcodes astronomers use to identify chemical elements, that are mysteriously broadened or skewed, hinting at forces beyond our current models. A handful of theorists whisper about dark matter interactions, where hypothetical particles collide with galactic gas to produce faint, anomalous glows. While still speculative, these ideas remind us that every odd color in the cosmos could be a clue, a breadcrumb leading to physics we've yet to imagine. What makes these outliers so invaluable isn't just their strangeness, but their refusal to fit neatly into boxes. A galaxy that's ultraviolet bright today might be infrared dominated tomorrow, its colors evolving with the violence at its core. Some flicker unpredictably, their hues changing over weeks rather than eons, challenging our notions of how quickly cosmic environments can shift. Others, like the infamous green bean galaxies, glow in a single, narrow wavelength of green due to ionized oxygen, a phenomenon so rare it wasn't even recognized as a distinct class until volunteers in Galaxy Zoo spotted them hiding in plain sight. The lesson here is clear: the universe's color wheel is far vaster than we've dared to dream. Every anomaly forces us to reconsider what galaxies can do, how they evolve, and what invisible forces might be shaping them. As telescopes grow more sensitive, we're not just finding new colors, we're discovering an entirely new vocabulary of light, one that's rewriting the rules of cosmic storytelling. And somewhere in that chromatic chaos between the ultraviolet flares and polarized jets might lie the next great revolution in how we understand the cosmos. The next generation of telescopes won't just observe galaxies, they'll decode them. Imagine instruments so powerful they can dissect the light from a single distant galaxy into thousands of individual wavelengths, each one a clue to its history, composition, and fate. The Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, will revolutionize this field with a field of view 100 times wider than Hubble's, capturing millions of galaxies in unprecedented detail. But it's not just about quantity. Roman's infrared capabilities will pierce through cosmic dust like never before, revealing the true colors of galaxies that have been hidden since the dawn of time. And when paired with ground-based behemoths like the extremely large telescope, with its 39-meter primary mirror, we'll achieve resolutions sharp enough to spot individual star clusters in galaxies billions of light years away, essentially giving us a time machine to watch galactic evolution in real time. What makes these tools so transformative isn't just their precision, but their synergy with cutting-edge spectroscopy. Future instruments won't just tell us a galaxy is blue or red. They'll identify the exact elements present in its stars, gas, and dust, down to trace amounts of rare metals. Picture reading a galaxy's spectrum like a chef analyzing a complex recipe, each absorption line revealing the ingredients forged in supernova or stirred up by black hole winds. Some teams are even developing hyperspectral imaging, which combines traditional color data with layers of chemical and kinematic information, turning each galaxy into a multidimensional puzzle. This could solve mysteries like why certain galaxies age prematurely or how black holes influence their hosts' colors in ways we've yet to grasp. Then there's the AI revolution. Machine learning models trained on simulated galaxies and existing datasets will soon predict how a galaxy's color should evolve based on its environment, mass, and star formation history, flagging anomalies that might signal new physics. Imagine an algorithm spotting a galaxy that's too red for its age, hinting at a previously unknown quenching mechanism, or detecting a subtle ultraviolet glow that betrays a hidden population of stars. These tools won't replace human intuition, they'll amplify it, sifting through petabytes of data to highlight the cosmic needles in the haystack, the most exciting prospect. Discovering colors we can't yet categorize. Just as Webb revealed galaxies with unexpected infrared signatures, future telescopes might find hues produced by exotic stellar populations or even unknown physical processes. Could there be galaxies tinted by dark matter interactions, or ones whose light is polarized in strange ways by primordial magnetic fields? The universe's palette is far from fully explored, and every new instrument brings us closer to reading its full spectrum of secrets. This isn't just about sharper images or prettier pictures, it's about rewriting the story of cosmic evolution. With these tools, we'll watch galaxies transition from blue to red in unprecedented detail, catch black holes in the act of altering their hosts' colors, and maybe even spot the first generation of stars whose light has never been seen before. The language of galactic hues is about to become fluent, and what we learn could change everything we know about the universe's past, present, and future. A galaxy's color isn't just a pretty facade, it's a ticking cosmic chronometer measuring eons with the precision of atomic decay. Picture a sprawling spiral galaxy glowing electric blue. That vibrant hue isn't artistic license, it's the unmistakable signature of stellar youth, where massive stars burn hot and fast, flooding their surroundings with ultraviolet radiation. These stellar adolescents dominate a galaxy's light output, their intense energy skewing the color spectrum toward shorter wavelengths. But time works its inevitable magic. Within a few 100 million years, a blink in cosmic terms, these blue giants exhaust their nuclear fuel, exploding as supernova or collapsing into dense remnants. What remains are smaller, cooler stars that glow with the reddish tint of aging embers, shifting the galaxy's overall color toward crimson. This transition from blue to red is so predictable that astronomers call it the galactic color magnitude relation, essentially nature's own aging scale for star systems. The real power of this cosmic clock emerges when we compare galaxies across different epochs. Take the Large Magellanic Cloud, our Milky Way's satellite galaxy. Its irregular shape and patchy blue regions betray ongoing star formation, marking it as relatively young compared to the reddish, smooth ellipticals found in dense galaxy clusters. But the true revelation comes when we look deeper into the universe and further back in time. Surveys like the Hubble Ultra Deep Field show that the early universe was dominated by blue galaxies. Their frenetic star formation rates 100 times greater than what we see today. As the cosmos aged, the balance shifted. The once blue universe gradually reddened as star formation slowed and galaxies matured. What's fascinating are the exceptions that prove the rule. Some galaxies appear too red for their distance, suggesting they aged prematurely. Others, like the famous blue blobs found in galaxy clusters, stubbornly cling to their youthful hues despite harsh environments that should have quenched their star formation. These outliers aren't mistakes in the cosmic clock, they're evidence of the violent processes that can accelerate or delay galactic aging. A collision between two gas-rich galaxies, for instance, can trigger a burst of new star formation, temporarily reversing the reddening process like a cosmic fountain of youth. The most precise timekeeping comes from spectroscopy, splitting a galaxy's light into its constituent wavelengths. Hidden in those rainbow bands are absorption features that act like atomic clocks, revealing the prevalence of certain elements forged in stars. Younger galaxies show strong signatures of oxygen and neon, elements produced abundantly in short-lived massive stars. Older systems display prominent magnesium and iron lines, products of longer stellar evolution. By measuring these subtle differences, astronomers can date galaxies with astonishing precision, often narrowing their star formation histories to within a billion years. Remarkable accuracy for objects billions of light years away. This color clock technique has rewritten our understanding of cosmic dawn. The James Webb Space Telescope's discovery of surprisingly red galaxies in the very early universe suggests some galaxies matured incredibly fast, forming most of their stars before the cosmos was even a billion years old. Meanwhile, certain dwarf galaxies in our local neighborhood appear frozen in time, their blue colors indicating they've barely changed since the universe's youth. Each data point adds another tick to the cosmic metronome, helping us reconstruct the universe's grand evolutionary timeline, not through theoretical models, but by reading the actual light emitted across the ages. Perhaps the most profound implication is what this tells us about our own Milky Way. By analyzing its composite color, a subtle blend of blue star-forming regions and redder central bulges, astronomers have pieced together its history, multiple epochs of star formation, mergers with smaller galaxies, and gradual settling into its current spiral form. We're not just observers of this cosmic clock, we're products of its relentless ticking, living in a galaxy whose present hue encodes its entire past. And as we continue to refine these techniques, who knows what other temporal secrets the universe's palette might reveal? Our eyes are remarkable instruments, finely tuned by evolution to perceive the world around us, but they were never designed to read the universe's full story. The visible spectrum we see, from deep violet to vibrant red, is just a sliver of the electromagnetic symphony playing across the cosmos. Beyond that narrow band, galaxies whisper in ultraviolet, shout in X-rays, and hum in radio waves, each wavelength carrying information our biology simply can't access unaided. It's like trying to appreciate a grand opera while wearing earplugs. You might catch the melody, but you'd miss the harmonies, the counterpoints, the layers of meaning woven into frequencies just outside your grasp. This sensory limitation isn't just a minor inconvenience, it fundamentally shapes how we've understood the universe for centuries. Early astronomers like Galileo, peering through their rudimentary telescopes, saw only the visible light of stars and nebulae, unaware that entire dimensions of cosmic activity were hidden in the infrared glow of dust or the gamma-ray bursts of colliding neutron stars. Even the iconic Hubble Deep Field image, which revealed thousands of galaxies in a patch of sky no larger than a grain of sand held at arm's length, captured less than half the story. The galaxies in that image weren't just the blues and golds we see. They were also radiating torrents of invisible light, their full stories locked away in wavelengths our eyes can't decode. Enter technology, humanity's great sensory translator. Modern telescopes don't just magnify distant objects, they extend our perception into realms evolution never prepared us for. Take the Spitzer Space Telescope, which specialized in infrared. Where our eyes see darkness, Spitzer revealed nurseries of newborn stars shrouded in dust, their heat signatures glowing like embers in the cosmic night. Or the Chandra X-ray Observatory, which exposed the violent hearts of galaxies, where supermassive black holes rip matter apart at temperatures of millions of degrees, emitting high-energy X-rays that paint a picture of chaos invisible to optical telescopes. These instruments don't just show us more, they show us differently, remapping the cosmos in colors no human eye has ever witnessed. The magic lies in how we translate these invisible signals into something we can comprehend. False color imaging assigns visible hues to non-visible wavelengths, turning ultraviolet into vivid purple or infrared into deep red, creating a visual language that bridges the gap between the cosmos's complexity and our perceptual limits. But this isn't just artistic license, it's a careful scientific process. The colors chosen aren't arbitrary. They preserve the relative energy of the light being detected, allowing astronomers to read the images as naturally as they would a visible light photo. A galaxy that appears green in a composite image might be radiating intensely in both ultraviolet and infrared, with the green hue signaling a balance between star formation UV and dust emission What's truly revolutionary is how this expanded vision has reshaped our cosmic narratives. Before infrared astronomy, we thought elliptical galaxies were red and dead, their star-forming days long past. But when infrared telescopes like James Webb peered through their dust, they found hidden reserves of gas and even pockets of newborn stars, forcing us to revise our theories of galactic aging. Similarly, ultraviolet observations revealed that some seemingly quiet galaxies are actually seething with young, massive stars, their light absorbed by interstellar dust and re-emitted as infrared, a revelation that solved the mystery of why certain galaxies appeared anomalously bright in one wavelength but dim in another. This technological augmentation of human perception isn't just about collecting data. It's about expanding the very boundaries of our curiosity. Every time we build a telescope sensitive to a new wavelength, we're not just adding another tool, we're opening a new chapter in the universe's autobiography, written in a light we've only just learned to see. And as our instruments grow more sophisticated, who knows what other chromatic secrets the cosmos might yield? The universe has been speaking to us all along, not in a whisper, but in a spectrum of voices. Now, thanks to technology, we're finally learning to listen. Galaxies are cosmic shape-shifters, constantly rewriting their own stories through color. Picture a vibrant spiral galaxy, its arms awash in the blue glow of newborn stars, a celestial beacon of youth and activity. But given enough time, that same galaxy might transform into a smooth, reddish elliptical, its star-forming gas exhausted, its stellar population aged into quiet retirement. This metamorphosis isn't just a visual change, it's a fundamental shift in the galaxy's very nature, etched into the wavelengths of its light. the journey from blue to red begins with the stars themselves. Massive hot stars burn blue and bright, but their brilliance is fleeting. They explode as supernova or collapse into black holes within tens of millions of years. Smaller, cooler stars, by contrast, glow faintly in red hues but endure for trillions of years, outlasting even the galaxies they inhabit. Over time, as a galaxy's blue giants die out and aren't replaced, its overall color shifts toward red, like a forest transitioning from spring's fresh greenery to autumn's muted tones. This aging process isn't always steady, though. Some galaxies experience sudden bursts of star formation, reigniting their blue hues temporarily before fading again, cosmic flashes in the pan that leave behind clusters of aging stars. Mergers add another layer of drama to this transformation. When two spiral galaxies collide, their gas clouds compress, triggering a firestorm of new star birth that paints the system blue. But the violence of the collision can also funnel gas toward the supermassive black holes at their cores, igniting quasars whose fierce radiation blows away remaining star-forming material. The result, a galaxy that might have burned blue for billions of years instead rapidly quenches, its color shifting to red as star formation shuts down. The antennae galaxies, locked in a slow-motion collision, showcase this beautifully, their tangled arms speckled with blue star clusters, while their cores begin the inevitable reddening. Environment plays a starring role too. Galaxies in dense clusters often age prematurely, their gas stripped away by encounters with neighbors or the superheated plasma between them. Like crops withering in a drought, these galaxies redden faster than their isolated counterparts, their star-forming fuel stolen before it can be spent. Meanwhile, in the cosmic boondocks, galaxies drift in near isolation, conserving their gas and prolonging their blue phases for eons. The Virgo cluster, packed with red ellipticals, stands in stark contrast to the blue spirals dotting the sparse Lynx Cancer void, a testament to how location dictates destiny. Yet some galaxies defy expectations. The so-called blue ellipticals challenge the notion that all smooth, round galaxies must be red and dead. These rare objects, like the striking NGC 3218, combine the shape of an ancient elliptical with the color of a young spiral, suggesting recent gas accretion or a delayed star-forming burst. Even more puzzling are the rejuvenated galaxy systems that somehow reignite star formation after billions of years of quiescence, their colors flickering back to blue like a dying flame given new fuel. The true power of this color coding lies in its universality. By comparing galaxies across cosmic time, astronomers have reconstructed the universe's demographic shifts. Billions of years ago, blue galaxies dominated, their star formation rates 100 times today's levels. As the universe expanded and gas grew scarce, the balance tipped toward redder, older populations. But the story isn't linear. Outliers like the blue nuggets in the early universe or the Green Valley galaxies in our backyard remind us that galactic evolution is a tapestry, not a timeline. What's emerging is a dynamic portrait of galactic life where color serves as both clock and compass. A galaxy's hue reveals its past collisions, its star-forming habits, even the density of its neighborhood. And as telescopes like James Webb peer deeper into the past, we're catching these transformations in action, watching as the universe's palette evolves from the brilliant blues of youth to the deeper reds of cosmic maturity. Far from static snapshots, galaxies are living canvases. Their colors a language we're only beginning to translate. Between the vibrant blues of youthful galaxies and the deep reds of aging ones lies a fascinating middle ground, what astronomers call the Green Valley. This isn't just a random transition phase. It's a cosmic balancing act where star formation isn't too rampant or too dormant, but just right. Picture a galaxy teetering on the edge of two destinies, one path leading to a fiery burst of new stars, the other to a quiet, gas-depleted retirement. These galaxies are like celestial tightrope walkers, and their delicate equilibrium holds secrets about how the universe regulates the birth and death of stars. The Green Valley gets its name from the way these galaxies appear in color magnitude diagrams nestled between the blue cloud of star-forming galaxies and the red sequence of quiescent ones. But don't let the term green fool you. Their hue is often more of a subtle yellowish white, a blend of fading blue starlight and emerging red giants. What makes them so intriguing is their star formation rate, not the explosive bursts of a spiral galaxy's arms, nor the near-zero output of an ancient elliptical. Instead, they're churning out new stars at a moderate pace, as if the galaxy itself is pausing to catch its breath before settling into old age. Scientists believe these galaxies are caught in the act of quenching, the process by which star formation shuts down. But unlike the abrupt halts seen in cluster galaxies, where external forces like ram pressure strip away gas, Green Valley galaxies seem to be quenching from within. Some might be exhausting their fuel naturally, their gas reservoirs dwindling after billions of years of star formation. Others could be feeling the influence of their central black holes, whose energetic outbursts heat or eject star-forming material, gently putting the brakes on new stellar birth. Then there are the outliers galaxies that appear to be rekindling star formation, perhaps after merging with a gas-rich neighbor or absorbing fresh material from cosmic filaments. The real value of studying these galaxies lies in their transitional nature. They're the missing link in galactic evolution, offering snapshots of the mechanisms that turn blue spirals into red ellipticals. Take the Milky Way's neighbor, Andromeda. Once a blue star-forming powerhouse, it now sits comfortably in the Green Valley, its star formation slowing but not yet stopped. By dissecting its light, astronomers have found clues about how supernova explosions, black hole activity, and even the galaxy's own structure contribute to this gradual winding down. But the Green Valley isn't just a one-way street. Some galaxies appear to linger there far longer than models predict, as if some unseen force is stalling their transition. Others flicker back and forth, their colors shifting slightly as star formation reignites in fits and starts. These anomalies challenge the idea that quenching is a straightforward process, hinting at a far more dynamic and nuanced galactic life cycle. What's emerging is a picture of galactic aging that's less like a steady decline and more like a series of adjustments, a cosmic thermostat fine-tuning star formation in response to internal and external cues. By decoding the rules of this equilibrium, astronomers aren't just learning why some galaxies fade while others flare. They're uncovering universal principles that govern how all galaxies, including our own, mature over time. And in that delicate balance between blue and red, the universe might just be hiding its most profound lessons about growth, change, and the inevitable passage of cosmic time. Step into any planetarium, and you'll see galaxies painted in broad strokes, blue spirals, red ellipticals, as if the universe worked with a limited palette. But the truth is far more dazzling. Galaxies come in hues that defy simple categorization, their colors blending and clashing in ways that reveal the complex physics at play. Take the Sombrero Galaxy, for instance. At first glance, its bright core and dark dust lane might suggest a typical spiral, but peer closer and you'll notice an unusual golden white glow, a signature of its unique mix of ancient stars and thick dust rings, like a cosmic antique gilded by time. Then there are the misfits that refuse to fit neatly into color categories. The green pea galaxies, discovered by citizen scientists in the Galaxy Zoo project, are tiny but radiant emerald spheres, their intense green hue coming from ionized oxygen lit up by furious star formation. These compact powerhouses pump out ultraviolet radiation at rates that dwarf larger galaxies, their unusual color betraying their extreme nature. Equally puzzling are the purple Galaxies systems where the red light of aging stars mingles with the blue glow of residual star formation, creating a regal twilight shade that hints at a galaxy caught between two life stages. The real marvel is how these colors correlate with a galaxy's structure and history. Blue spirals like the pinwheel galaxy showcase sweeping arms alive with young stars, their vibrant tones tracing the density waves that compress gas into stellar nurseries. Red ellipticals, such as those in the Coma cluster, tell a different tale, their uniform crimson hue whispering of quiet stellar graveyards where star formation ceased billions of years ago. But even these broad trends have exceptions. Some ellipticals hide blue cores, evidence of late-life gas accretion or cannibalized dwarf galaxies, while certain spirals sport reddish arms, their star formation quenched by encounters with neighboring giants. Diversity extends beyond visible light too. In ultraviolet, starburst galaxies like Messier 82 become blazing beacons, their cores searing with the light of newborn stars. Infrared unveils the hidden warmth of dust-shrouded giants such as ARP 220, where colliding spiral arms glow like cosmic embers. And in X-rays, the true violence of galaxies like Centaurus emerges, its jet-spewing black hole painting the surroundings in high-energy hues invisible to human eyes. Each wavelength adds another layer to the story, proving that a galaxy's color depends entirely on how you look at it. Cataloging this cosmic rainbow isn't just an exercise in aesthetics, it's a vital tool for understanding galactic evolution. When astronomers plot galaxies on a color magnitude diagram, patterns emerge like constellations in data. Most fall along the red sequence or blue cloud, but the outliers, the two blue ellipticals, the two red spirals, hold the keys to unsolved mysteries. Why do some galaxies age prematurely? How do others defy their environment, staying stubbornly blue in regions where neighbors redden? The answers lie in the subtleties of their light, the slight shifts in spectrum that betray hidden black holes, ancient collisions, or streams of infalling gas. What's clear is that the universe has no single recipe for galaxy formation. From the sapphire brilliance of a young spiral to the ruby glow of a relic elliptical, each color tells of a unique path through cosmic time, a narrative written in starlight, waiting to be decoded. And as our telescopes grow more sophisticated, we're not just seeing more galaxies, we're learning to read the finer print in their chromatic stories, discovering nuances that challenge our expectations at every turn. At the heart of nearly every galaxy, including our own Milky Way, lurks a supermassive black hole, not as a passive vacuum, but as an active sculptor wielding unimaginable power. When these cosmic giants feed, they don't just consume quietly, they belch out torrents of energy in the form of high-speed winds, capable of reshaping entire galaxies. Picture a hurricane tearing through a forest, only instead of trees, these winds rip through interstellar gas, the very raw material needed to form new stars. The aftermath, a galaxy that might have blazed blue with youthful stars, instead begins to redden prematurely, its stellar nurseries dismantled by forces emanating from its own core. These black hole winds aren't gentle breezes, they're supersonic tempests, racing outward at millions of miles per hour, heated to temperatures that make the sun's core seem chilly. As they sweep through a galaxy, they perform a cosmic balancing act, On one hand, they can compress gas clouds in their path, briefly igniting bursts of star formation that paint spiral arms blue. But more often, their sheer violence overheats or outright ejects the galaxy's gas reserves, starving it of the fuel needed to make new stars. Over time, without fresh stellar generations to maintain its blue hue, the galaxy's color shifts toward red, like autumn leaves signaling the end of a vibrant season. The most dramatic examples come from quasars' galaxies where the central black hole is actively feasting. The quasar Markarian 2319 offers a stunning case study. Observations reveal twin jets of particles screaming outward at nearly light speed, while surrounding gas glows in X-rays from the wind's intense heating. The galaxy's overall color tells the story: patches of lingering blue star formation near the edges, but a core increasingly dominated by older, redder stars as the black hole's influence spreads. It's a snapshot of galactic transformation in action, where the supermassive black hole isn't just an occupant, it's the architect of its host's evolution. But here's the twist: these winds don't always spell doom for star formation. In some galaxies, like the nearby Centaurus A, the black hole's outbursts appear to trigger star birth in select regions. As the winds slam into surrounding gas, they create shock waves that can compress cool gas pockets into dense knots, collapsing them into new stars. This paradoxical effect means a single galaxy might display both the blue of newborn stars and the red of quenched regions simultaneously, a chromatic tug of war between creation and destruction. The real breakthrough in understanding this process came when telescopes like the Atacama Large Millimeter Array began mapping the cold gas in galaxies undergoing black hole feedback. They revealed intricate gas filaments, some being blown outward like cosmic streamers, others falling back inward in a slow-motion cycle of destruction and renewal. These observations solved a long-standing puzzle: why some galaxies shut down star formation entirely, while others merely throttle it back. The difference lies in the wind's power relative to the galaxy's gravity. Stronger winds can completely expel gas, leading to rapid reddening, while weaker ones might only heat the gas, delaying but not extinguishing future star formation. What makes this research so pivotal is its connection to the broader universe. Galaxies in dense clusters, where black holes are often active, tend to be redder than their isolated counterparts, a pattern now attributed in part to black hole winds working in tandem with environmental effects. Even more intriguing are the implications for the early universe, where supermassive black holes grew to enormous sizes remarkably quickly. Their winds might explain how some galaxies became red and dead astonishingly early, while others, perhaps spared the full brunt of feedback, remained blue star factories for billions of years longer. The next frontier, understanding how these winds interact with dark matter, the invisible scaffolding of galaxies. Some theorists suggest that particularly powerful outbursts might not just affect a galaxy's gas, they could alter the distribution of its dark matter halo, reshaping the gravitational landscape that guides the galaxy's future growth. It's a reminder that when we observe a galaxy's color, we're not just seeing starlight, we're reading the latest chapter in an epic story of gravity, energy, and time, written in hues that span the rainbow of cosmic evolution. Somewhere in the cosmic shadows lurk galaxies so faint they barely qualify as galaxies at all, vast, ghostly structures where stars are almost an afterthought. These are the dark galaxies, celestial phantoms made mostly of dark matter, their sparse gas and meager starlight stretched so thin they're nearly invisible against the blackness of space. Spotting them is like trying to photograph a whisper, yet their elusive color signatures might hold answers to one of the universe's most stubborn puzzles. Where is all the missing matter we know should exist? The challenge begins with their composition. Unlike typical galaxies where stars outshine everything else, dark galaxies are dominated by dark matter, that mysterious substance that doesn't emit, absorb, or reflect light. What little visible matter they contain often takes the form of diffuse hydrogen gas, too spread out to collapse into dense star-forming clouds. The result: a galaxy that might span thousands of light years but glows with only a fraction of the luminosity of a single star cluster in the Milky Way. To telescopes, these objects often appear as nothing more than faint smudges, their light drowned out by the brilliance of nearby stars or the glow of Earth's atmosphere. Yet even these cosmic ghosts leave traces. Their hydrogen gas, though sparse, emits a telltale radio signal at a specific wavelength, 21 centimeters, a faint but detectable heartbeat that betrays their presence. Some, like the famous Dragonfly 44, were discovered precisely this way, not by their starlight, but by the way their gas interacts with the faint cosmic background radiation. Others reveal themselves through gravitational lensing, their dark matter bending the light of more distant galaxies like a phantom hand distorting a reflection. The colors of these galaxies, though subtle, are equally revealing. Without the blue blaze of young stars, their light skews redder, tinged by the feeble glow of whatever ancient stars they manage to form. Some exhibit a strange greenish hue in narrowband filters, a signature of ionized gas excited by ultraviolet radiation from rare, massive stars or even hidden black holes. Others show patches of unexpected blue, suggesting brief, localized bursts of star formation like flickers of lightning in a vast, dark sky. What makes these faint glows so valuable is their connection to the universe's missing baryons. According to our best models, there should be far more ordinary matter, protons, neutrons, and electrons, than we've observed. Dark galaxies, with their reservoirs of pristine gas, might be hiding a significant portion of this lost material, tucked away in forms too diffuse for traditional telescopes to spot. Their very existence challenges our assumptions about how galaxies form, suggesting that star formation isn't just inefficient in some corners of the cosmos, it's practically dormant. The hunt for these phantoms is pushing telescope technology to its limits. Instruments like the Square Kilometre Array, designed to detect ultra-faint radio emissions, promise to uncover thousands of dark galaxies lurking in the voids between brighter structures. Meanwhile, space-based observatories like Euclid are mapping distortions in starlight caused by dark matter's gravity, potentially revealing dark galaxies by their shadowy influence rather than their light. But the real prize lies beyond mere detection. By studying the color gradients and gas dynamics of these elusive objects, astronomers hope to crack open one of cosmology's biggest mysteries: how dark matter shapes galactic evolution. Some dark galaxies appear to be failed versions of normal ones, their gas too stirred up by cosmic winds or too starved of density to form stars. Others might be cosmic fossils, relics from an era when the universe was too young and smooth to birth galaxies efficiently. And a few could be the building blocks of today's giants, waiting to collide and merge with brighter neighbors, their dark matter providing the gravitational glue for future star formation. Every faint hue, every whisper of radio static from these shadowy systems is a clue, not just to their own nature, but to the hidden architecture of the universe itself. In their dim light, we might finally find the missing pieces of a puzzle that's eluded us for decades, written in colors so subtle they're almost invisible. The color shifts of distant galaxies are far more than a visual spectacle. They're a cosmic language revealing the universe's past, present, and future. Imagine each hue as a word in an ancient manuscript, written not in ink but in starlight, waiting for us to decipher its meaning. From the deep redshift of galaxies fleeing into the cosmic void to the unexpected greens and purples that hint at violent collisions or hidden black holes, every shade holds a story. These aren't just static snapshots, they're dynamic narratives of stellar birth and death, galactic mergers, and the invisible tug of dark matter shaping everything from afar. What's astonishing is how much we've already decoded. A galaxy's color can tell us its age: blue for youthful stellar nurseries, red for aging stellar graveyards, or reveal its environment, like the premature reddening of galaxies trapped in dense clusters. It can even expose the fingerprints of black holes, whose furious winds heat gas to X-ray brilliance or quench star formation entirely, leaving behind a galaxy that's redder than its years. But for every mystery solved, new questions emerge. Why do some galaxies flicker between colors like cosmic chameleons? How did certain ancient galaxies grow red so quickly? The answers are hidden in the subtlest shifts of light, waiting for sharper tools and sharper minds to uncover them. The future of this cosmic detective work is brighter than ever. Telescopes like the upcoming Nancy Grace Roman Space Telescope will map millions of galaxies in unprecedented detail, while AI sifts through the data for patterns no human could spot. Spectroscopy, once limited to nearby galaxies, will probe the chemistry of the most distant objects, revealing elements forged in the universe's first stars. And as we peer deeper into the infrared with instruments like James Webb, we'll uncover galaxies so ancient their light has been stretched into near invisibility, each one a time capsule from the cosmos's infancy. This isn't just science, it's a conversation across billions of years. When we analyze a galaxy's color, we're not just collecting data, we're listening to the universe tell its story. And the more we learn, the clearer it becomes. Every shade, from the faintest red to the most vivid blue, is part of a grander narrative about how galaxies live, evolve, and eventually fade. So the next time you look up at the night sky, remember, those pinpricks of light aren't just pretty dots. They're sentences in a cosmic epic, written in a language of color we're only beginning to understand. If you've enjoyed this journey through the secret language of galaxies, hit like, subscribe, and let us know in the comments which cosmic mystery fascinates you most. The universe is still speaking, and together we'll keep translating its story, one hue